Hey, this is Steven from RC Engineering, and welcome to my very first video of my Rule of Thumb series. So in this Rule of Thumb series video, we're going to be talking about DC motors. And so these first few videos are going to be talking about some general engineering principles, which are common throughout planes, cars, and boats. So DC motors are used on planes, cars, and boats all together. And for example, the next video would be something like batteries, and the video after that would be something like gearing. So in this video, we're going to be talking about brushless versus brushed motors. Their graphs. So we're going to look at power, torque, amps, efficiency, and RPM graphs, and seeing how we could leverage some of these in real world testing to leverage these motors to do what we want them to do, to run, like for example, max speed or max efficiency. Okay, so we're going to spend about maybe a few minutes talking about brushed versus brushless motors. So here I'm on OneNote. I have a few articles posted on here, and also a few graphics and a few graphs to go over, also some equations to go over some of the engineering principles. So basically what this article says, and you should see my cursor here, is that basically the difference between brushed and brushless motors is that the brushless do not have brushes. That sounds, pretty straightforward, but they lead to a lot of different properties. And basically, in a nutshell, the brushless has poles that an ESC or electronic speed controller switches on and off to spin a rotor around in a circle, while a brushed has brushes that ride on a commutator that switch the polarity that attracts one side to a magnet, and then switches the polarity and then repulses it from the same magnet. So here we see brushed motor advantages. Simplified wiring: brushed motors can be wired directly to DC power and controlled by as simple as a switch. So what that means is the ESC just has to control how much current goes to the motor, and that controls speed. But generally this happens on an ESC by doing what's called PWM, which is pulse width modulation, which means that it sends full voltage at a certain frequency that will simulate speed of a motor. So basically imagine you're in a room and you're switching a light switch on and off very quickly. If you switch it on and off fast enough, it will actually give you the illusion that the light is dimmed, even though you're giving it full on and full off all the time. And that's how it works, the motor. And they use that through a transistor. However, with a brushless, you have to have complex timing that turns poles on and off, or turns poles on and off at a certain time. Otherwise, you'll have problems. Otherwise, you'll have weird vibrations and you'll destroy the motor. So very, very complex software and hardware is required to run brushless motors. So brush motors' disadvantage are less efficient because you have brushes that are actually contacting and rubbing on something. So you have friction, which is a loss, which is we don't want. Electrically noisy because of the switching action of the polarity all the time will send some electromagnetic noise. Also, lifespan is very small. Sometimes some of these brushed motors, you'll see an average lifespan of the small ones, like 8.5 millimeter can motors, which is what I use quite a bit. Those only get a lifespan of like 5 hours of flight time, and then that's it. Because most of these motors for RC, you cannot replace the brushes. Bigger ones on cars and boats, you can. Smaller ones for planes, not really. So if you could replace the brushes, then you'll get way better lifespan, but you'll have to replace the brushes all the time. Brushless motor advantages: long lifespan, no brushes to wear out; low maintenance, no brushes to replace; high efficiency, high initial cost; need for a communicating device like an encoder and a driver controller. So that basically means that you have to have a sensor inside that tells the ESC where the location of the rotor is, and so that it knows which pole to switch on later. And here's the main part: brushless motors are typically 85 to 90% efficient, whereas brushed DC motors are around 75 to 80% efficient. So the main thing is that they're more efficient. Brushless motors need more complex ESC that has special timing and special programming inside, and also special hardware. while while brushed can just be simply plugged into a wall socket to be full on. A wall socket, of course, that's converting AC to DC, and you could also control it by just switching on and off the current that goes to it, or switching on and off the voltage that goes to it. So here are two displays of the brushed. This guy's the brushed. And this is BL or brushless. Now the brushless, you have these on these here that go around here. This is the rotor, and these are permanent magnets. While these guys all the way around, there's 1, 2, 3, 4, 5, 6. Those are electromagnets. So those could be switched. The magnetism can be controlled by switching them on and off, while the permanent magnets are always magnetized. So what happens is you have two different poles, the north and the south pole. The south pole is attracted to the north pole, and the north pole is attracted to the south pole. North poles repulse each other, and south poles repulse each other. So here, for example, let's say that the orange is the north pole and the green is the south pole. So you have a green here and a green here, orange here, orange here. So what happens is the ESC will turn on this pole and this pole, as the ESC can only control the electromagnets, which are along the outside ring here. So what happens is when it turns on this at this polarity, this electromagnet at this polarity, this orange will be attracted to that green, and this will move to this position. This electromagnet is also on with an opposite polarity of the green, so the green will also move here. And then this scenario will keep going on and on and on forever, while the ESC will turn off this pole and turn on that pole. Turn off that pole, turn on that pole. On and on forever and ever. And as you see, you need 1, 2, 3, 4, 5, 6. So you need to do that 6 times per revolution, while some of these are 50,000 RPM, right? So you're thinking times 6, so that's 300,000 times per RPM that this guy has to switch. So you could calculate per second how many times the ESC actually has to switch the pole. So it requires a lot more processing on board of the ESC. Now the brushed is way simpler than that. As you see here, we have brushes. These are the red guys here. And these guys are attached to the battery. And the battery keeps a constant plus minus. That polarity doesn't change. But if you notice here, the commutator is this green arc. And you see it actually has like a gap right there and a gap right there. And you see that it's also wired to each of these armatures, to each of these coils. So what happens is as these brushes go around, it's only in contact with one commutator at once. Then another one will come in and attach. So what happens is it'll actually, sometime in the rotation, this will be a positive polarity, and sometimes when it's in a different contact to the other commutator, this is a negative polarity. So positive or negative. So what happens is you can imagine that you have a polarity where it is currently set up where if this guy was rotating this way, as you see, is rotating here, this guy is attracted to the North Pole, and then the commutator switches, and now it is repulsed from the North Pole. Same thing here, it is attracted to the South Pole, and then repulsed from the North Pole. And as you see, the timing is controlled physically on the on the brushed motor itself. So the only way the brush timing could be off is if it was designed incorrectly. So you don't have to worry about that. You just have to feed power to it and it will turn. Whether or not you want to control the speed, now that is a little bit more complex, but it's just a simple PWM through a transistor compared to an ESC where it needs to do either looking at the back EMF on the motor to figure out where the stator is or any sort of other complex timing. So most things that you're going to see in RC is going to be brushless. So I'm going to go over a few of what the numbers are. I'm sure you've seen them when you go and look at brushless motors. So first main ones are these ones here. You got 2-2 and 1-2. 2.2 is the motor or rotor diameter. Most of the time it's the rotor diameter in millimeters. So this rotor here, so this is an example of brushless rotor, this rotor would be 22 millimeters in diameter. Let's just say that that was a 2212. And then a 12 means that the rotor is also 12 millimeters thick or height. So the dimensions of the rotor are 22 millimeters in diameter and 12 in height. Then you have the very important kV. kV means rotations per volt. So they don't have a very good standard here. Generally the K means 1,000. So usually this would mean 850 times 1,000. So it's 850,000 revolutions per volt. But that's not the case. This company actually means 850 times the voltage. So sometimes on some you'll actually see where it's correct and they'll say 0.850. Or some, like for example, some brushed ones will be 17 kilovolt. That means you take 17 and multiply it by 1,000 and then multiply it by the voltage. So you have to kind of use your better judgment to figure out which one's correct. So, I mean, it's probably not spinning 800,000 RPM times 5 volts, right? It's probably not spinning 4 million, revolutions per minute. So just use your better judgment on that. If it's a really small number, it probably needs to be multiplied by 1,000. Really, really small, like 17 or 30, something like that. Or in this case, it would be 0.85. And if it's a really big number, you probably don't multiply it by 1,000. And then these guys are number of electromagnets. This one you probably don't see as much. Number of electromagnets in stator. So that means here you have 12. So that means that you have 12 of these guys right here, the electromagnets that the ESC turns on and off. Then it says number of permanent magnets in rotor. And so it says here 14. So that means you have 14 inside the rotor. The orange and the green ones inside the rotor. These ones right here. This one and this one. So that means you would have 14 of those permanent magnets in there. Now here's what I was talking about. RPM is you take the kilovolt rating and you multiply it by the voltage, and that is your RPM max. That means that is as fast as the motor could spin at that particular voltage with no load applied to it. So no prop, no tires, no impeller. Alright, so we're going to go into a few graphs, the actual engineering portion of this video. So here we're going to talk a little bit about a generic graph that I have here, and also a actual motor. And the BL means brushless, so it's a brushless DC motor. So if we look here, we see that a few different things are plotted. We have the power arc, we have the efficiency line, and the torque and amps line. And this guy is measured in percentage. RPM is the percentage in the x-axis, and the percentage of whatever is labeled is in the y-axis. So what we'll actually see is that we can look at a few things here. We notice that the power is actually like an upside down parabola. Efficiency is estimated as a line up to about 90%. And torque is just a straight line down. So let's take a look at this really quick. 100% RPM means that we have 0 torque, 0% RPM, which is our stall speed. Stall means basically the motor is no longer moving, is 100% torque and amps. They're kind of related. So the more torque you get, the more amps you're drawing generally. So if we're at 0 RPM, we're getting 100% of our torque, our rated torque. And we see that at max power, we're hitting max power at about 50% RPM. 50% RPM and 50% torque and amps, and also 50% efficiency. That's when we're hitting max power. Now let's look at efficiency. At efficiency, we're somewhere around 90% RPM range. And we're hitting a very low, about 15% torque, and something like 50% power. So at 50% power, we're getting we're getting like 82. It maxes at about 82% efficiency. And then over here you see some equations that I wrote for it. Power percentage is a parabola, upside down parabola. 1 over 25 times x minus 50 squared plus 100. X is the RPM. Torques, or amps, percentage is equal to negative x plus 100, as is estimated as a line. Efficiency percentage is x, while x is less than 90. So, looking at that, let's go ahead and look at a real example of an actual motor that has been tested in real life, as this is an ideal or typical motor performance. So let's take a look at the brushless. Alright, so looking at this guy, we see this guy is actually opposite of the first one because of how it's arranged. But you'll see that the chart is exactly the same, or the graph is exactly the same as the other one. Even though this is a real life one and this is an ideal one, they're pretty much the same. So we could estimate most of our motor performance as a rule of thumb, that's where the series name comes in, as the typical motor response. So this is our rule of thumb. This guy here is the rule of thumb that we're going to be looking at. So let's take a look here. So current, red, power, watts is green. Watts is also the engineering measurement of power, which is basically voltage times current, otherwise known as joules per second. Okay, so efficiency is in blue, efficiency is in percentage, speeds in RPM, current is in amps. So let's take a look at this. So here we see that efficiency maxes at about, what do we say here? 87, I'm going to say about 87%. We're looking somewhere around here, 87%. And it lowers all the way down at stall speed, which is the maximum torque. Let's look at stall's max RPM is about 550 or something, 5050, something like that. Maximum power, we're looking at how many watts. Our maximum wattage is about 160 watts. Max current is about 15.5 amps. And yeah, and then also what you'll see as well is that most manufacturers will give you a rating of where they suggest the motor to be used. And that is this dotted line right here. This is the dotted line down here, rated torque. So this is where they want you to run it. They want you to run it at about 85% efficiency, at about 120 watt power, at 4 amps, and at 4,000 RPM. So that's where they want you to run it at. Alright, so let's take a look. At 87% efficiency, let's say we wanted to maximize efficiency. What are we looking at? We're looking at about 4,500 RPM. We're looking at about we're looking at maybe 65 watts. And again, that's pretty close to 65, or it's pretty close to 80 watts, like 70 watts. So 80 watts is 50% as from our rule of thumb. So that's pretty close. So our rule of thumb is pretty close to actuality. Then we're looking at also amps. So max amps is about 2.5 amps. So that's if we wanted to run our motor at maximum efficiency. Maximum and we're running, that's pretty fast. Maximum power, again, we went over that already. So what we're actually going to do now is we're going to go over where this efficiency comes from, and then we're going to go over some actual motors and see what happens when we manipulate that data to get what we want. So here, talking about efficiency. Efficiency engineering is generally known as power out over power in. So this is also known as work out over work in. So for example, on a prop, this would be labeled as thrust, how much thrust you get for how many watts you put in. And for a car, it would be like torque times RPM or whatever over watts. And for a boat, it would also be the same, torque over watts. Similar. because both air and water are both fluids, so it's technically the same thing. You can think about it. So where do a few of these inefficiencies come in? Copper loss, which is basically the wire that you use as the winding in the motor has a resistance that is known as an ohm inside the wire. So what the manufacturer of the wire will give you is they'll tell you it's a certain number of ohms per feet of wire. So to know this, you would actually need to measure the resistance of the motor. So you could just check, the positive side, the negative side, and then look at the resistance, and it will tell you. And that resistance is RW. So the more current you feed through, the more, basically what this is this is how many watts are lost. So it does actually take power just to push current through a wire and do nothing, right? Unless you want to heat something, right? So this is lost as heat. So the more current you feed through a specific resistance of wire, the more heat is lost. So the more current your motor draws, the more loss you get. And we see a little bit of that up here, where the more current we're pulling, the less the efficiency drops. So as current goes up, efficiency goes down. Then you have iron loss. Basically what iron loss is the minimum amount of power you have to put into a motor to get it to spin at all. So so for example, if you had a graph, and let's just have a little offset here. So let's say this is 0 RPM, and then this is like 5. It's actually, and then this is the watts. It's actually going to take a little bit of watts just to get it to start turning. And so this is the iron loss. How much energy or how much power you have to put into a motor to get it to start to move, right? And all electronics have this. They have a minimum power rating that they need to even turn on, right? So that is what this is. Voltage times current is equals to watts, right? And I0 is the initial current or the minimum current, unloaded current. That means no load on it. So that's what it is. Iron loss, minimum amount of power needed to get the motor to turn, to do anything, to get any work out. So basically it's this guy, it's workout. So to get like 0.0001 workout, it'll take like, let's say, 2 watts in. So that's the inefficiency they're talking about. And then here's the general efficiency equation. Now this is just the efficiency of the motor. Remember, we're also going to have inefficiencies of prop, for example, propeller inefficiencies, impeller inefficiencies, tire and friction inefficiencies, drag, all different types of other inefficiencies that are going to account for this. This is just for the motor. And then also you have battery inefficiencies, electronic speed controller inefficiencies. You're generating heat all over the place that is not used for work. So there's inefficiencies all over the place. So let's talk a little bit about a specific motor application. This is a airplane application. This is an Emax motor, MT2204. So that means that the size, and you see here that it says the size of the can, otherwise known as the housing, is 27.9 millimeters, but it says it's a 22. So that must mean that this rotor is 22 millimeters in diameter inside. Then it says 04, which means that, and obviously it's more than 04 tall, so that must mean that the rotor inside is 4 millimeters tall, or 4 millimeters long. Then we see here our kilovolts are 2300 kilovolts, so obviously we're going to use our intuition and assume that we don't want to multiply that by 1000, because then, that's not going to be right. Then we see down here that we have some actual data that has been tested in the field. We see a current of, here we see 8 volts applied with a 6x3 prop. 6 means the inches in diameter the prop is. 3 means the pitch. And the 3 generally means that per rotation, if all inefficiencies are ruled out, the plane would actually move 3 inches. That's what it means. So for every twist, so basically you have 3 inches of twist. but we call it pitch, right? That will also be going over in the rule of thumb video on propellers. Current 6.4 amps. Thrust, which is a force, which means basically how much weight you could lift. For example, if you were going straight up, you could lift 240 grams straight up. So 240 grams. Power, wattage, which is current times the voltage, is 51.2. And efficiency, again, remember, right here, work out over work in. So what type of work are we trying to do? We're trying to produce thrust. So the thrust over our work in is equal to a ratio of 4.7 to 1. Speed, RPM, 11,910. So let's go ahead and apply this to our rule of thumb knowledge and see where they are on the efficiency curve and other things. So what we do is we do the basic math. 8 volts, which is our applied voltage, multiplied by 2300 RPM, 2300 kV, is equal to 18,400 RPM. Then we take this is our maximum RPM with no load. We put that on the bottom, and then we put the stated RPM on the top. And then we multiply that by 100 to get a percentage, and we get 64.7% out of max RPM. So from the maximum RPM that we could go, we are 65% there. So let's go ahead and go to our rule of thumb graph. And with 65%, that means that we're somewhere around here. Let's look at where we are. So here we see that we should be getting using our graph here. So 65 negative 65 plus 100 is equal to 35. So we're at 35% of our total torque. And for efficiency, efficiency is just X, so we're at 65% efficiency, right? So that's pretty good. We max out at 82, but that's a brushless, so we should be maxing out at 90, so we're pretty low at 65% for that particular 6x3 prop. And we are looking at 65% RPM, as that's what we solved. So pretty low number, probably because we're very low inside of the RPM range. We're not high enough inside the RPM range, and we're not high enough getting towards the peak of the efficiency curve. But this is also not calculating for the inefficiency of the prop, which is 240 grams. So we're just looking at the efficiency of the motor in this video. So there's also inefficiencies in the prop. So that's probably also why we're seeing very low efficiency. Next one, I looked at the 12 volt, looking at a 5x3 carbon fiber prop. Current is going up, thrust is going up, but watts almost double. Efficiency is dropping. So let's do the math on this and see where we are on the curve. 12 volt times 2300 kV is equal to 27,600 max RPM with no load. We take their found RPM, 20,000 times 20,100 over our max RPM at 12 volt, 27,600 RPM times 100. We're looking at 72% of our maximum RPM. Let's go to our rule of thumb graph. And we should be somewhere around here. So let's go ahead and look at this. And we notice that we are actually more into the efficiency curve than normal. So why is our efficiency lower? Because this efficiency is said to be 3.4 grams per watt. Reason being is from this copper loss. We are starting to pull more and more amps. So as you double your current, your inefficiency increases by 4 times, as this is squared. 2 squared is equal to 4. So we want to pull as little current as possible. So the more current we pull, the less our efficiency drops. And we also see that with the exact same prop, our efficiency drops because we almost doubled our current, right? But we see that also we are probably closer to max. Actually, we're way lower than max RPM. So we're somewhere around probably the 65%. So it is a function of the iron loss, copper loss. Iron loss, we can't fix that. Copper loss, we can fix that by not pulling as much power. So let's look at something. So these guys did not really use the curve very much. I'm sure that they did. They had their own engineering principles. But let's look at something that really uses this rule of thumb to its advantage to get very high efficiency. As this motor here is probably built more, the Emax 2204 is built more for speed than it is efficiency. So let's look at something that uses that curve, that rule of thumb curve. This is a tiny little 7mm by 16mm canned brushed motor. And if you see here, it actually has a reduction gear. And we'll go into, I'm going to talk a little bit about why that's a good deal here, and then we'll also go into it more in the gearing rule of thumb video. So we see that we have a few different test data, but we also see that it gives us the RPM, not in kV, but it says 40,000 RPM at no load, and then it gives you the voltage. So you just take that number and divide it by the voltage, and then that will give you your kV. Obviously, it's like 13333, 13333 kilovolt, and then you just do that. So now that's kilovolt, 13.3333 kilovolts. And then the suggested prop. However, we cannot use the equations that we were using on the Emax because it does not give us a stated test RPM. It only gives us the RPM at low load. Down here in the test data, it does not give us any RPM at that time. So here we're using a 50-30. Basically what that means is a 5x3. So 5-inch diameter prop by 3-inch pitch. And the different voltages, the current ratings for each corresponding ones, the wattage, which is the current times the voltage. And it gives us the thrust. And wow, look at that. 12.36 grams per watt compared to the maximum here of 4.7. So that's almost 3 times the efficiency, right? 2.5 times, somewhere around there. So what would that mean? So that means if you had a plane or a car that got that much more efficiency, you would be able to fly if they had the same exact battery pack, same exact current pull, everything. If everything was, only difference was these two motors, but everything else was kept the same, you'd be able to fly for 2.5 times more length. 2.5 times more longer. 2.5 times longer. But as you see, the more current we pull, our efficiency drops. Right? Now we're using a smaller prop, 4.5-inch diameter prop by a 3-inch pitch. We see a voltage of 3.8 and 4 volt, 0.81 amp, 0.87 current, watts 3.5, thrust 32 gram and 35 gram. Efficiency max 10.4. Reason being is that we'll learn in the prop video that the bigger prop you go with, generally the more efficient it is. But these are great numbers. And so before I end this video, I'm going to talk about how they did that to get the efficiency. And as you know, this is good efficiency because this is a brush motor compared to this guy, which is a brushless motor, which brushless are more inherently more efficient. The key is how they used the gearing. Now if we look up here, basically what they did is they have the motor run at peak efficiency and then down the speed through a reduction gearbox. And we'll learn in the gearbox video that when you have a reduction gearbox, which basically means the motor has a smaller gear on it than the gear that turns whatever you want to turn. So as you see down here, the gear that turns the prop, which is that guy, is quite a bit bigger than the gear that is attached to the motor. So that is a reduction gear. If it's the other way around and you have a bigger gear on the motor and a smaller gear on whatever you're turning, that is a up gear, I guess you could say. So you have a reduction and then an up gear, I guess you could call. So they're running the motor in max efficiency, and then when you do a reduction gearbox, depending on the size / the tooth count of the difference, right? So for example, let's say that one on the motor has 5 teeth, and the one on the end gear has 50 teeth. That is a 50/5, otherwise known as a 10-to-1 gearing ratio. So what that means is your RPM will drop on the output by 10 by 10. So for example, since down there it said 40,000 RPM, max RPM, you divide that by 10, that means you're only getting 4,000 RPM on the output shaft. What that also means is that your torque will increase by 10. So basically, it's like moving this guy back 10 times. So back over towards this area somewhere. So now you're getting the efficiency of something that has very little to no torque, but yet the torque of something that is getting like 25% efficiency. So they're getting the best of both worlds. Because of that, they could use a small motor to turn a very large prop, and they get the maximum efficiency that the motor has possible. And that way, they get the maximum efficiency that they were looking for. So you could imagine this efficiency if they just swapped it to a brushless. This would be, get up into maybe the 15s. Anyways, this is just a little coverage of this topic. We're going to be doing more stuff with this, especially for planes and cars and boats. So for planes, obviously, what you're attaching to is a prop. So we'll also look at prop inefficiencies. And then we'll look at batteries as well. And then in inclusion to the rule of thumb series, we're also going to be doing some real life testing of this theory. We're going to put some motors head to head. I will be building a test stand to test these against each other, so we can see in actuality with our own eyes what this looks like numerically as far as results. So then after we do the results, we're going to build our own planes, cars, and boats, and then test and then have some fun with it in real life and get maybe faster speeds or longer flight times or whatever we decide to do. Alright, so this has been Steven from RC Engineering. I'd like to thank you guys for watching my first video in my rule of thumb series for RC Engineering. I will see you guys in the next video. I'd like to thank you guys for watching. If you like this video, please subscribe for more videos like it in this series and other series as well. And I will see you guys in the next video. Have a good day. I'll talk to you guys later.